All right, this is the video key for the Unit 11 review. Some of these things that I'm going to explain, some of them I'm just going to sort of leave up to you to read and ask me if you have any questions about them, because I think that the text that's on the page does a pretty good job of explaining the concept for itself, but always feel free to come in and ask me if you have any more questions on any of these things. So, for instance, this whole section A, number 1, coming up with these definitions, those are things that you can all sort of just read through and let me know if you have any questions about what they mean. So I'm just going to move on to the concept questions. Concept question number 2 here, it says, which of the following would cool down faster, a piece of wood at 50 degrees Celsius or a piece of aluminum at 50 degrees Celsius, assuming that they're the same mass, and how do you know? So to understand this, you have to think about the heat capacity. We talked in class about slides that were made out of metal and how those tend to heat up easier or faster and things like that. And so you look on your table of heat capacities and you see that all metals have a pretty low heat capacity. It's easy to heat them up and cool them down, versus wood is a little bit higher. It's 1.8, I think. And so wood ends up being something that's harder to heat up. And so looking at this, then we're going to say that the aluminum is going to cool down faster than the wood. So looking at question number 3 here, it says, which of the following holds more thermal energy, a kilogram of water or a kilogram of copper metal? In this case, this is also related to the specific heat capacity. Water is going to hold more energy, and this actually goes to the literal definition of specific heat or specific heat capacity. When we use the word capacity, we mean how much can be held inside of something, and so when we say heat capacity, we mean how much heat can be held inside. The specific part of that is per gram, okay? The word specific in science oftentimes means per gram. So specific heat capacity is how much heat can be held in a substance per degree Celsius per gram of the substance. And so water, having a much higher heat capacity, can hold more heat in it than the copper metal can. Number 4 here, thinking about this one, it says you mix 2 substances together and they heat up, surprisingly or suddenly. Is it endothermic or exothermic? In this case, if they're heating up, that means that they're giving off heat. You're feeling heat come off of them. So that means that it's going to be an exothermic process, and exothermic processes have negative signs for their Q and their delta H because energy is leaving the system in that case. Question number 5 here is talking about if you put ice out on the sidewalk and what would happen, and would this increase or decrease the entropy of the universe? So most of you should expect that if you put ice out on the sidewalk and it was a hot summer day, that ice would pretty quickly melt. That hopefully makes sense to most of you. And so that's what you'd expect to happen. And then the answer to the second question has to do with the second law of thermodynamics, which says the entropy of the universe is always increasing, meaning that the universe is proceeding towards a state where things are gradually more and more disordered. And along with that, we know that any spontaneous process, any process that's going to happen normally and naturally, requires an increase in entropy for the universe. And so, so that means in this case, if it's something that is normal and natural for us to see, then it's probably something that is going to increase the entropy of the universe. In fact, if it happens, if anything happens, any process, anything that you ever observe or experience in life, it's always increasing the entropy of the universe. Going on to question number 6 here, it says, is it possible for a system to become more ordered according to the second law of thermodynamics? It is possible for a system to become more ordered because a system isn't the entire universe, all right? So we can get a relative amount of order or organization within a system, but that comes at the expense of a large amount of disorder being created in the surroundings. And then when you add those together, the system plus the surroundings, the entropy of the universe still always increases. So if you think about it this way, maybe, your room at home might be relatively disordered because it gradually just proceeds that way, right? As time goes by, things get messy, things get out of place because you're just kind of randomly throwing things around. You could take some time and organize your room and put it in, into a good organized state. But the act of doing that actually causes a lot of disorder because, for instance, it requires energy from you, and as you burn calories, you're breathing out carbon dioxide molecules, and that's spreading out the carbon dioxide all over the place, and so taking carbons out of your bodies, and it's distributing heat because you're also generating heat as you work and things like that. So the entropy of the universe still increases. It's this inescapable thing that's always happening. Entropy is always increasing, but the universe includes both the system and the surroundings. For question number 7, it says, what's the main purpose of the Styrofoam cups in the calorimetry lab? What assumption does it allow us to make? So in that lab, the Styrofoam cups, and we actually used 2 of them, they're meant to make it so that it's an insulated container that this reaction is happening in, or that this process is happening in. And the whole purpose of that, say when we put a metal inside a calorimeter, is to make sure that no heat can get outside of the vessel or get into the vessel. And that means that anything that is lost by one substance inside, say like you're putting the copper inside, any heat that's lost by the copper has to go into that other stuff. It has to go into the water because it can't escape the container. And so the assumption that comes from that then is that the heat lost by the copper is equal to the heat that's gained by the water and vice versa. And so if that's the case, then we can set up that whole negative mc delta T equals mc delta T equation that we use for all of our calorimetry problems. So having an insulated container is actually very important to calorimetry. Okay, now I'm going to go through these 3 problems at the bottom here. I'm actually going to open up a separate set of slides to do that so that you can see the whole process of me working them out. So I'll go ahead and do that right now. All right, so this is problem number 1 on the back there. And what we've got here, it says 25 joules of heat was added to 1.5 grams of silver, and it wants us to find the initial temperature here. It's given us the final temperature. So to do that, we have to start out by saying delta T equals Q over MC, which equals 25 joules over M, which is 1.50. And then we have to look up the C for silver. If you look it up on your table, you should find that it's 0.237. In this problem, we have 2 sig figs on the top and then 3 sig figs times 3 sig figs. And so our answer should have 2 sig figs. For the delta T, I get 70 degrees Celsius, so it's 70 degrees Celsius, because it should have 2 sig figs. And then you have to keep in mind that the delta T equals T final minus T initial. All right, and so we know delta T is 70 point. All right, and that equals our T final. We're given that 125, and minus T initial here. And so if you go through and calculate that, you should get that Ti equals 55 degrees Celsius. For problem number 2 here, this is a calorimetry problem. So we start up negative mc delta T equals mc delta T. If you read through there, you should see that it's looking for the mass of the water. So we have everything else. So we'll set this up negative 55.0 times C. This one, it should say actually, it should say iron twice here. It says lead, but we're looking for iron in this case. So for C, it's 0.444 for iron. Delta T, the iron here, it goes from 150 degrees Celsius down to 32.7. So the delta T that we have is negative 117. Pay attention to sig figs there. It goes up to the ones place. That equals mass of the water is what we're trying to find. C for water is 4.184. Delta T for the water, it goes from 22.2 to 32.7, which is an increase of 10.5. All right, simplify both sides here. We get 2,857.14 equals 43.93 m. All right, divide both sides by 43.93. We get m equals 65.0 grams. And this should have 3 sig figs. And the way that you know that is you look back at that original long line with that equation in it, and you count the sig figs and everything, and you see it's 3 and 3 and 3 and 4 and 3. So our answer should have 3. All right, now on to the last one. This one here is one of those enthalpy problems where we're given something, we're asked how much heat is released or absorbed. So the first step there is you want to make your path. So we go from molecules to moles to Q. Going from molecules to moles, the conversion factor is 6.02 times 10 to the 23rd. Going from moles to heat, our conversion factor is delta H in the ratio. All right, so that's kind of what we're going to be doing here. So we'll set that up. We've got 9.55 times 10 to the 22nd molecules of water. And then we know that there's 6.02 times 10 to the 23rd molecules of water in 1 mole of water. And then we look here at the balanced chemical equation, look at the coefficient on the water, we see that it's a 1. So we know for every 1 mole of water consumed, there are 65.2 kilojoules released. Run that through, calculate it, your answer should have 3 sig figs in the end. We get 10.3 kilojoules released. All right, and that is that.